right. Good morning. Morning. So let me tell you who I am, and I'm going to ask who you guys are because it's not 100% right on there. My name is Michelle Cramer. I currently teach at Albright College, and this is my first year in the grant. So you guys, I guess, are all veterans, right? You guys have all been through this before. All right. A little bit about me. My background is I have a BS from Shippensburg in chemistry. Any Shippensburg people? Darn. All these teachers and no Shippensburg people. And my grad degree is a Master's of Science from UVA, University of Virginia. And then I also have my teaching cert in high school chemistry. I actually worked for about 7.5 years as an industrial research chemist. After I got my cert, I actually found my industrial job first and did that until I had my daughter and retired. And then finally went back into academia after she was a couple years old. So this is going to be my 4th year at Albright. Going into my 4th year. So you guys are a mix of high school and middle school. All right. How many chemistry people do I have? I've got the couple, and I was going to say, I knew the shoes. I love the shoes. The Tom shoes, yeah. All right. But you guys at least have all had chemistry. Anyone not have a college chemistry class? Okay, a couple of you guys. All right. So some of this material, unfortunately, for some of you will be very old hat, and some of you, you're going to have to kind of hang with me a little bit as we go through it. And we're going to, talk about what I have to cover in terms of the standard. You guys all know some of this basic information. I have this for the other groups as well as, things that I typically teach, like my non-majors classes. Chemistry, when we're talking about chemistry, obviously, the study of the matter and the transformations it undergoes. Oh, I also apologize, I forgot one thing. I do have my phone on. My mother is currently in intensive care, has been for over a week at this point. I have the phone on in case the hospital needs me, that they can call. So if I bolt, I apologize in advance, but other than that, I try to stay focused as much on this as I can. So we're going to talk about chemistry. Now, did you guys have the other 2 chemistry sessions yet? Either of them? Just one. Which one did you have? Mailers. Okay. So you did redox. Okay. All right, because you're also going to do Lewis dot. So for those of you who haven't had it for a while, it's probably good that you have this first anyway. It'll help you with that for sure. All right, I always like to talk a little bit about why study chemistry. For you guys, it's not as critical. You guys are all science teachers, right? So you all like science, and I don't have to convince you to like science. But the key thing with chemistry, obviously, chemistry is all around us. It's in everything from our bodies to the air we're breathing to the chairs you're sitting on. And sometimes it's important to remind the students, regardless if it's other teachers or even your students, of that fact. And just the fact of, we're breathing air. The only reason we can breathe the air is because it contains the chemicals that we need to sustain our life, things like that. And of course, it's the central science, and I know some of you who aren't chemists would argue that it's not. But if you...
The physics teachers always say.
The physics teachers, of course, yeah. But if it wasn't for the electrons, we couldn't talk about electricity in physics, right? So we'll go there. And of course, the big thing when I'm talking especially to the non-majors or to the elementary teachers and trying to convince them why chemistry is important, you want to be a more informed consumer. And as you're teaching your students, that you're trying to at least educate them to have some basic understanding of science and how science is important to them. And ultimately, chemistry is fun. Now, I will give you the caveat with what's going on this week. The way I'm going to handle the week is I'm going to give you all the core curriculum today. We're going to cover all the topics we need to cover. The second session, I will not be here, and it will actually be a hands-on, like watching a video and then doing some hands-on activities on the iPads and some problems and things like that. So we'll get that set up. But I am going to try to plow through this, as quickly as I can. Most of you who should recognize most of this material anyway, so it shouldn't be too bad. So let me tell you what standards I'm focusing on. The standards I'm focusing on deal with the atomic structure and periodic table, and primarily the behavior of electrons in atoms. So some of this we have to give you some basic definitions if you haven't talked about chemistry for a while. But then we're going to go in and talk specifically about electrons. We're dealing with things like ground state electron configurations. We're dealing with orbital diagrams. All right? And ultimately, in the end, we're going to talk a little bit about emissions spectroscopy and what we see when we look at an atomic emissions spectrum. Yes? This will be on the wiki space, yes. It's not yet because I only got approved this morning, but I can now post, so it will be sometime today. Thank you. Yeah, so in terms of the notes, and you're going to see some of this is very fundamental. You don't need to be taking notes on its review for you guys. Some of it's going to be a little more detailed. All right, so I can't just jump in and talk about electrons, right? I need to give a general context to this. So the first thing we talk about is atoms and elements. And of course, atoms. Atoms have been around since the beginning of the universe. And I like what they presented at Goddard because it talks about the formation of the stars and the formation of how everything began. So basically, you have the fact that all your elements beyond hydrogen and helium really ultimately were initially produced in the interiors of the stars. All right, and we saw that a little bit while we were down there, and you'll see pictures of the nebula and different things that are going on that relate to that as well. The other thing I like to point out, and we'll talk about this as we go on, is that atoms are mainly empty space. All right, and you don't think about it that way, but hopefully you'll get an understanding of that as we talk. So of course, we've got our elements. We've got the periodic table of elements. Everybody hears the word, not everybody knows what it means. But element, of course, is a material that only contains one kind of atom. So for instance, if you have a piece of gold, it's pure gold, it only contains gold atoms. If you have white gold, it's not pure gold. It's a mixture. It's a homogeneous mixture. All right? If you have a diamond, it's pure carbon. All right? And it's the elemental form of carbon as well. Of course, some of our atoms, and our atoms are the fundamental building block of all elements. So basically, you can think of this elements used to talk about macroscopic quantities. You can see a piece of gold. You can see, you can dig and find iron ore, right? That's a macroscopic quantity. When you talk about atoms, we don't see atoms. They exist at the submicroscopic level. So you can't even look at them with your biological microscopes. You have to go to very high-tech microscopes to be able to visualize and see what the atom looks like. So of course, atoms make up everything that's around us. And to date, there's 116 distinct types of atoms. And those are the atoms that we find as the elements on the periodic table. All right? 90 are found naturally. And the remainder are synthesized. And obviously at this point, the new ones that are all being created are all the synthetic new materials as well. And again, there's just a reminder, an element, a material containing one type of atom. All right, so we have to talk about electrons, but we can't talk about electrons without talking about everything else that's there. So we have our atom. What's at the center of our atom? The nucleus that contains the protons and the neutrons. All right, again, figured for you guys this is old hat, but we need to talk about it. So, of course, protons have a positive charge, +1 charge. All right, same quantity of charge that the electrons have, but the electrons have what kind of charge? Negative. All right. The key with the protons, and also when we talk about the neutrons, is that they both are massive, and they are massive, very massive compared to the electrons. All right, still minutely massive compared to anything we can relate to, but they have the significant amount of mass, which tells us that the mass in an atom is contained in the nucleus of that atom. All right. Of course, if we're talking about an electrically neutral atom, we have the same number of protons as we do electrons. And finally, we can figure out the number of protons in an atom if we know its atomic number, or if we know the number of protons, we can tell what atom we're talking about, what element we're talking about. So of course, then we've got our neutrons. Electrically, they are neutral. So they've got that name, right? Again, they contain mass. So again, the mass in the nucleus is the protons and the neutrons. And the neutrons act as like the nuclear cement. And by the electrical forces and the strong nuclear forces hold the nucleus together. All right? Both the protons and neutrons collectively are called nucleons. You may have heard that term before. All right? And it just means they reside within the nucleus. Okay, so electrons, of course. Electrons are all identical. So if you have an electron in carbon, it's the same as an electron in gold. They don't change because of the material they are in. What charge do they have again? -1. So if you put two electrons together, what's going to happen? They're going to repel. All right? So of course they repel each other, and they also then repel neighboring atoms, because of course you've got the nucleus and you've got the electrons surrounding the nucleus. And as the atoms get closer together, those electrons get closer together and start to repel one another. All right? And again, neutral atom, number of electrons equals number of protons. All right, so here's a schematic. And as those of you who teach this know, it's hard to find a good schematic for this because none of them are correct. So we have this nice visual that shows our atomic nucleus and shows our electron cloud. But of course, what's wrong with this picture? Is the scale right? Yeah, the scale is way off. And of course, anything we visualize, the scale is going to be way off. So one of the relationships I like to use is if you think of a ballpark, Citizens Bank Park, the Link, something like that. And if you have a garden pea, you put your garden pea into your stadium. The garden pea is your nucleus. The stadium is the electron cloud. Okay? Does anyone else have any good analogies they like to use? Sometimes you can do that. I think the basketball to the earth is another one. Basketball is the size of the nucleus. The earth would be the electron cloud. You know, that's a little harder still to visualize because we don't have a good visual of what the earth looks like. The ballparks we all have seen at least, right? All right, so and there we are again, remembering the nucleus contains those positive protons and neutral neutrons. All right, so periodic table. So you will have a copy of this periodic table for the post-test, and unlike the pre-test. It will be a copy of this periodic table, not your copy, obviously, but you'll be given a copy. Actually, what happens is, depending on the scientist or the lab where it's formulated, typically they get those names at this point. Livermore is a laboratory, I believe, maybe in the UK. I'm not exactly sure where, but that's where that one got its name from. As you look back at some of the earlier ones in the seventh period, you're going to see things like Seaborgium, named after Glenn Seaborg, who's a Nobel Prize winner. But if you think historically, Mendeleev originally came up with the periodic table, right? And he came up with these arrangements of elements. And it's interesting, if you look at his arrangement and you look at the periodic table today, how on he was with it, including the fact that he left some holes where he didn't know that there was no material that existed, but he thought something should based on the properties he knew. And also, you can also see some of the evolution of the names. You go back, you find things like gold with its symbol AU because of Arum, or iron, Fe, because of ferrous, yeah. So the naming nomenclatures, the way the nomenclatures worked has evolved over time. But now typically, like I said, is more in honor of a person, in honor of a place, something like that. Okay? So my opinion of periodic table is we don't memorize the periodic table. All right? The main reason being, if it's great if a student can tell you Mercury is Hg, but if he doesn't know anything about it. Livermore, California. Oh, there we go. I knew it was a lab, but I thought it was the UK as well. But yeah. Okay. So it's actually California. Cool. So it's a U.S. synthesized. Hey, it was made in the USA. That's pretty cool. Thank you. Again, and some of you may still have your students memorize things, and it's fine. Just the more important thing is obviously being able to use the periodic table as a tool. So I like to teach people how to read the periodic table and how to use it to figure out what they need to figure out. This is a version that we actually do use at Albright, and this is the version that the majors all have, and use on the tests, and the non-majors as well. So I teach them how to use this and read it. It kind of relates to a dictionary. We don't memorize the dictionary, but we all know how to use one. So if we can make our students more educated on how to read the periodic table, we're going to be better off in the long run. All right, so here we've got another pictorial view of the periodic table. And of course, this illustrates some of the big properties that we can look at. First of all, the fact that we have on the left side, we've got our metals. And of course, on the upper right side, we've got our nonmetals with those little green guys in the middle. Okay, those are the metalloids. And what kind of properties do the metalloids have? Both, yeah. They have properties of metals and nonmetals, okay? So you can see, even in the fundamental just metal-nonmetal separation of the periodic table, you can see that you could be able to predict properties if you knew where something was located on the periodic table. You know, for instance, if you find your silver, and you can know that silver is a metal, and if you didn't intuitively know that, you poured hot water into your silver cup, what's going to happen to your handle? It's going to get warm because it conducts heat, right? And you know that because you know it's a metal and you know where it is on the periodic table, and you can make that prediction. So you could also predict that if you had, of course, a niobium mug and tried to, wanted to put hot liquid in that, what would you expect to happen? Same thing, all right? Again, because they're metals. We've got, of course, our gases on the upper right side as well. We've got our helium. So we know some properties of some of those materials because they're nonmetals. They tend to be gaseous. They tend to be some of the heavier liquids. Bromine, how many people have played with bromine? It's kind of fun, You got the fact that its boiling point's near room temperature, so you always have that brown cloud hanging out on top of it. Never breathe it. It's really dangerous for you. Kind of goes along with chlorine and why you can't mix chemicals. As you're cleaning the bathroom, don't mix anything with a bleach-containing chemical because it can generate chlorine gas, which will knock you out. The other thing, of course, we talked about the metalloids, have the properties of the metals and nonmetals, makes them good for the semiconductor industry. Okay? And that's why, silicon wafers, now germanium, they're moving into that a lot more. Again, but some basic things that we can learn just looking at the periodic table and where is an element. You can make some predictions about properties as well. All right, as we know, periodic table is very, very highly organized. This organization is the fact that we've got the vertical columns being called the groups or the families. We've got the horizontal rows being called the periods. So we can look at our periodic table and we see we have how many periods? 7. And we've got how many groups? 18. All right? So again, we'll see that within the groups, we're going to have certain properties that are going to be traits among the different elements in the different groups. We're not going to get as far as reactivity, but one of the main things that you find is that as you go down groups, your reactivity is fairly similar in a group or a family. Okay? Of course, periods, hence the name periodic table, we get the fact that you cycle through a whole period and then you come back and you start repeating properties. So you get that, you go through one cycle, come back and start a next period, and again, hence the name periodic table. So one of the periodic properties that we can look at is atomic radius. All right, and I just put this as an illustration of one of the properties that we can look at. It's not our main focus for today, but again, you can see here, you can see trends emerging. As you go down a group, what happens to size? It increases. As we go across a period, it decreases. So you can see these trends exist, and then you could ask questions like, which one would be larger, carbon or silicon? Again, if you have a periodic table, you could answer that question and tell me which one's bigger. Silicon. All right? So again, that's where learning to read the periodic table and to know some of these trends is most helpful. Here are some of our common names for some of our families. Okay, and some of these I'm sure you're familiar with. Obviously, we got the alkali metals, so your sodium and potassium, right? We got the alkaline earth metals, that's your calcium and magnesium group. We move over, we go through the transition metals, lots of changes. They're all kind of different, right? We got our halogens, chlorine, fluorine, bromine. And of course, on the end, we've got the noble gases. Anyone know why they were named the noble gases? Because they're antisocial. Exactly. Because the nobility doesn't like to interact with the common folk. And those elements, of course, do not like to interact with anything else. So I knew you guys would at least know that. All right, and of course, on this version of the periodic table versus the one I gave to you, this divides out a little bit differently. But we got these intertransition metals. We got the lanthanide group and the actinide group. And you will always see them on the periodic table separated out like this. I have a slide later that shows them put into place, and you see how awkward the periodic table becomes when you try to insert them in there. Just makes a copying nightmare. All right, so here's some useful tools. We're going to look at these quickly, and then on your next session, you'll be able to investigate these a little more. I'm sure some of you are familiar with the first one, Theodore Gray's periodic tables. Anyone see this before? In various forms. This is a great, great website. I have, there's the book. You can actually get the book through Scholastic for a while from the book orders. There are cards, like flashcards that you can assemble the big periodic table. You can build it on the floor. There's posters. I love this. It's an interactive periodic table. There is an app for it, but the app is $13.99. Yeah. I was going to say, I haven't gotten it yet, but I will because I have all the other stuff. The greatest thing about this is that it's interactive. So I'm going to pick my favorite element, osmium. It's what I worked with in grad school. So it's my favorite element. Interesting thing about osmium, density of water is 1 gram per cubic centimeter. It's the most dense material, 22.59. Extremely heavy, extremely dense. Okay? As you scroll down through this, if you've never been on this site, the cool thing that he does, Theodore Gray, collects samples of the elements. And he's got some very eclectic samples of elements. But he's got anything from, here's a sample from Everest, and it tells you where he got the things, which is kind of interesting, to the fact that, for instance, here's the osmium containing phonograph needle. So it gives you a lot of different things that you might not expect to see these materials in. This material here is osmium tetroxide. It's actually what I worked with in grad school. It's extremely poisonous and volatile, and we used to actually reflux it in rocket fuel overnight. So it's kind of an interesting mix of materials. But it's neat. Again, great tool if you do teach chemistry or teach physical science to engage the students, because they can go and they can do a lot of research on here. They can see all kinds of things. Like I said, you find all these random places that these elements are. All right? And you can do that with, any of the elements. And it's kind of neat. I like, he's got the people where they don't have, he doesn't have a sample. We've got oxygen in its blue liquid form, which hopefully you never see, right? Except on occasion, probably, huh? So that's a fun one. That's a real good one. As I said, for the iPads, $13.99 from iTunes. So, but you can also, if you order the book online from him, he autographs it, I believe, for my chemistry teachers. If you don't have the book, instead of to pay the extra money instead of ordering it from Amazon. Yeah, it's
Scholastic book fair. It was awesome.
It is. Yeah, I bought it, like I said, off my daughter's Scholastic order. So, the next one is actually a free app, and this is a really good one too. The Nova Elements app. Okay, that's a real good one to use. It's free. I like it because, again, it's interactive. It allows you to actually go on and build elements. So it lets you throw protons, throw neutrons until you start building things, which is kind of nice. It also has this, and I haven't played around with it a whole lot, but it's essential elements section. And in that section, it'll take an everyday material, and it'll let you build the molecules that are contained within that material. So again, kind of a neat twist on an app you can look at. Again, I'll give you some things to do with that for the next session as well. But that one's definitely worth the free download. That one's kind of fun to play with. Some of the others, as you look out there, be discerning, viewers and purchasers, because some of the stuff's not very good. As I was trying to find real good ones, it's hard, and it's hard to decide what's going to give you the information you want. So, all right. So I have a couple cartograms to show you. This is actually from a JChem Ed article. I can get you the reference if you want it. Showing various properties. And I like it just because it's a different presentation of the same material. It's colorful, So this is atomic radius, that same trend that we looked at. But here we see it in a cartogram where it bulges as the numbers go up. So you can see again the trend increasing as we go down, decreasing as we go across. All right, another nice visual. Now the next one is great, and my chemists will appreciate this. The abundance in the universe by the atomic number. All right, so you think about Earth, and we think about what we think about. And I think, if you'd ask someone what's the most abundant element, what do you think their most common answer probably would be? Oxygen, which is ironic because the air is really more nitrogen. I would say carbon, because you've got all the plants and all of our matter, that's carbon. But when you talk about the universe, it's hydrogen, because of course, what contains hydrogen? The stars. So on a universal scale, that's what we get. Helium's got its big blip as well. Not sure on the two little guys. I tend to think maybe we're getting into the carbon, nitrogen, oxygen. It might actually be a third one in there. I have to go back and actually read the article, but I just love the visual of the fact that hydrogen's the most abundant. And here's another one, and this is just kind of a neat one. Electron affinity deals with how much the atoms want to hold on to their electrons. And it's just a nice visual of that as well. So you can see there's different ways to present materials. Again, the bottom line is, though, that there's these trends in the periodic table. And it's not just haphazardly arranged, it's arranged for a reason. And you can see that as you start to investigate it more. All right. So now we're going to jump into quantum. And ultimately, I'm going to tell you where we're going with this and why we have to go through some of this. We are ultimately going to talk about electron configuration and orbital diagrams. So we've got to talk about quantum numbers, but we've got to get there. Okay? So, just bear with me as we go through this. Most of this should be somewhat fundamental, but not critical that you know the people, not critical, obviously, but just understand what's going on. And then when we get into the orbital diagrams, hopefully it'll make more sense. So we talk about quantum, and of course, most people when they hear quantum mechanics or anything like that tend to cringe because it's fairly high level math. Physicists maybe not quite as much cringing. So, but we start off, and you'll find a lot of this has a lot of physicists involved in it. We start off with Max Planck. Max Planck looked at this and said, he's got warm bodies. If they emit radiation, we got this radiant energy coming off. He actually called the little bundles of energy that were coming off quanta of energy. And he basically said that those energy in each of those little bundles is going to be proportional to the frequency of radiation. Now, remember, we're talking electromagnetic radiation, so the whole spectrum. What you're most commonly going to be thinking of course, is frequency in terms of the colors that you see. And it can be related to that, but again, remember the small portion of the electromagnetic spectrum that we're talking about there. We also have Einstein. Of course, Einstein looked at the light and said, well, light itself is actually going to be quantized. And he looked at it and said, okay, we've got these little beams of light. It's not a continuous stream, even though we envision it being a continuous stream. We don't see little particles. But he said it actually is all these little quantas of energy that he called photons. So we talk about a photon of light that's being emitted. So the question became, is light a wave or a stream of particles? It is both. So I know my physicists will know that. I know my chemists will know that for sure too, right? It is both. And basically what you have is, whenever you talk about this material, you're talking about models that are being used to describe things, to be able to relate it to things that we understand. But in this case, light can be described by both models. We've got properties of a wave, we've got properties of the particle. Both interact with one another, both are critical to your understanding of it. And again, when we talk about energy, the key is that this energy that we're talking about is going to be directly proportional to our frequency of light that we're talking about being generated. All right, so Niels Bohr took this, he used this quantum theory, and looked at this and said, all right, he's trying to explain what's going on in terms of atomic spectra. They could look at the stars and they could see these discrete bands of light coming off, being emitted from the stars, and what's going on. And he basically looked at this formation and said that we've got some kind of energy, and this energy is actually a potential energy that deals with how far the electrons are from the nucleus. So you can relate that, to potential energy, where you've got my phone up here, of course, has more potential energy than it does when it's down here. Same thing with the electrons. The further they are from the nucleus, the more potential energy they're going to have. All right? The other thing is that as we look at this, when an atom is taking in light, it actually is taking in energy in the form of that light energy. So it's absorbing energy. And what happens, of course, is that something that starts off lower takes off energy and goes which direction? It goes higher. You've increased the potential energy. So you've given it energy in form of a photon of light, and it's boosted the energy level of that electron. So of course, the converse of that is also true. If you take an energy that's at an electron that's at higher energy, and it gives off its photon of light, it has dropped in energy. And what Bohr basically said is that this has got to be happening at distinct energy levels. Okay, it's not haphazardly happening. It's got to be happening. These changes are very discrete, and it's not a halfway there, halfway not there. An analogy to this is, you walk up steps, right? You go from step 1 to step 2. Are you ever on step 1.5? No. Same thing here. We can't have an electron that's in that 1.5 space. They're going from that n equals 1, the lowest level closest to the nucleus. They're then taking a step up to the n equals 2. Again, when they come back down, they've got to fall the whole step down. They don't fall halfway down and get stuck in the middle. So these changes in energy then that we see is what we see as that distinct lines in the atomic spectrum that we're looking at. Okay? And hopefully we'll get to that. If not, we'll talk about that more in the follow-up as well. We'll try to look at least at a little bit at the emission spectroscopy aspect. The key is, again, though, it's got to be this full step. And you see this nicely presented here pictorially. You've got your nucleus. You've got an electron at a certain energy level. You go ahead, you put energy in the form of a photon of light. You've boosted the energy of that electron. Okay? And then, of course, as that electron loses its energy, it's going to give off a photon of light. And that's going to be at a very distinct frequency. And you're going to see that as the bands on the emission spectroscopy, emission spectrum when you look at that. All right. Bohr also used his model then to explain why atoms just don't collapse in on themselves. All right, it's good they don't because we wouldn't be here, right? So he basically said that, again, they can only lose energy in specific amounts, and they can only ever drop down to that n equals 1 level. They can't ever get any closer than that level. So you can think of that as the onion peel. You got the onion center is the nucleus, and you've got those layers, right? You can only get so far, and then you'd be in the center, and then you destroy your onion at that point. You destroy your atom at that point as well. But they never can fall in further than that. Okay, and of course, when they reach that lowest level, that's called the ground state. And we're going to talk about ground state electron configurations here in a bit. But again, lowest energy level, just like the ground level of a building. Okay, you can't go any lower than the ground level, even if that ground level is underground, right? Another model that was used, of course, is a planetary model. And again, each of the models kind of has its own limitations. And our understanding is based on the fact that we understand multiple models and we kind of put them all together. But we can look at this planetary model. And it's nice. We were just at Goddard and we saw the planets and learned why Pluto is no longer a planet because doesn't have that beautiful concentric orbit. So of course we've got the same relationship here. We've got our nucleus in the center like our sun, and we've got these energy levels going out like the orbits of the planets. All right. So again, it's just another visualization. It's kind of a simplification though, right? I mean, this isn't exactly what we're dealing with. It's not flat. They're not all in those, they're in nice concentric orbits, but they're not flat orbits. And what we end up having to consider is the fact that we said, light and electrons then have wave properties as well. So when we start talking about the wave properties, we end up starting to talk about probability of having electrons at certain spaces and things like that. But what we find is that, as I said, you don't have the electrons orbiting the atom in a very circular, flat path and planar path. As they're going around, they're actually doing their wave pattern. So if you would look at it side on, you'd see like a sine wave pattern being generated. All right? And what you find is that for an n equals 1, we've got a single wavelength occurring as that electron's going around. N equals 2, 2 wavelengths, and you can keep going on. Now, if you look at this, we can look at a wave machine. Any of my physicists have wave machines they play with? Okay. Let's say, because this is kind of a neat one. And you can see what ends up happening. If you have a finite amount of wavelengths, you're going to be able to have that reinforcing wave, and you're going to see that nice wave pattern being generated, right? they have to be whole increments, because as soon as they're not, what happens to your wave? You kill it. You know, that destructive interference, right? Starts going back on itself and it just kills it. So same thing is going on with the electron. The electron's got this specific wave pattern that it's following as it's going around the nucleus. Alrighty, so now we're going to talk about quantum numbers. All right. So ultimately, like I said, we have to get to ground state electron configuration. We have to get to being able to write that and understand that. So we're going to start off by talking about quantum numbers. All right. So first thing you need to know is that each element in its ground state has its own unique set of quantum numbers. There are 4 quantum numbers. I'm going to go over them with you in a minute or two here. Basically, what you need to know is that quantum numbers deal with the probability of finding an electron at a certain point in space. All right? And of course, you know, we're talking about the space outside the nucleus. And ultimately, then we can look at this and we can talk about the electron configuration for each of the individual elements. All right, so quantum numbers. Here we go. We got 4 we're going to talk about, right? The first one, of course, is the principal quantum number. It is indicated by an n. N is restricted to having only positive integer values. And what are those positive integer values, you know, mostly going to be? I'm not saying that there's not energy levels beyond this, but 1 through 7, all right, from the periodic table. All right, for what we need to talk about, obviously more than we need to talk about in 1 to 7. We're not going to get quite that far. All right, positive integer values, never 0. Okay, it's never 0. As n increases, the orbital increases. That planetary model, right? You go out from the nucleus, you start getting larger and larger in size as you're going out. And finally, then, of course, increasing the n means you're going to higher energy, higher potential energy. All right, that one's pretty straightforward. The next one, the angular momentum quantum number. And I should have fixed this and actually had a little script L, because we typically see it as script L's in our books. It usually has that, I'm sorry, I don't know that you guys can see that over there. Usually has that script L look to it. All right. It can have positive integer values from 0 through n minus 1. So if we have an n equaling 1, what is our L going to be? 0. If we have an n equaling 2, what can our L values be? 0 and 1. So all integer values from 0 through n minus 1. All right? Now, this defines the shape of the orbital. And it does that by having the fact that each of the L's is designated to have a letter used for it. All right? So you want to know this, understand this chart. If we're talking an L of 0, it means it's an s orbital. And you guys probably all have a visual of this, but that an s orbital is that nice, bless you, that nice spherical orbital. Okay? Of course, changing in size depending on what its principal quantum number is. All right? When we go to p's, we got those nice dumbbells, right? Of course, these are 3-dimensional space, so we can have 3 different p's. We can have one on the x, the y, or the z axis where it's coming out and going back to you, right? When we get into d's, we get into some funky combinations, right? We got the double dumbbells going in different orientations. And we've also got, I love the one with the, you know, the fat tire one. Yeah. Looks like a, you know, P, and it's got this like inner tube around it or something. Okay? You don't need to know the shapes of them, but I know that some of you are familiar with that, and it might refresh some things for you as well. But the key is that the angular quantum number gives you that shape. Because if you know that it's a 0, it's an s orbital, that would give you a visual of it's that spherical orbital that you're talking about. Okay? Anyone have any questions on the first 2? Okay. All right, the next quantum number we talk about is our m sub L, our magnetic quantum number. It can have integer values between negative L and positive L and include 0. So, for our first example here, what would our M sub L be? 0. You know, positive L to negative L through 0. For the L of 0 here, again, an M sub L of 0. But how about for that L being 1? What options do we have for M sub L? We have negative 1, 0, 1. All right? This talks about orientation in space. So this is what takes it from the fact that it's a p orbital to the fact that it's a px orbital or a py orbital. All right? The main thing, again, that you need to know is you need to be able to understand how to get from having an L to having an M sub L. I think what we would see, what you guys need to know for the test itself is, given a set of quantum numbers, are they correct? So you have to understand the rules. You know, and if you were given this example, is that correct or incorrect? It's incorrect because the L has to be 0, can't be 1. All right? So having an understanding of how you find the quantum numbers and being able to identify correct, incorrect is what you need to be able to understand. Okay? All right, finally, the last quantum number is the spin quantum number. And it can have a value of +1/2 or -1/2, which deals with spin up, spin down. And it just indicates the 2 directions of spin. All right? You don't have to do any calculation there. It's just what it is. All right, any questions on those two? All right, so we can look at this table. This is a table out of one of the texts we use. Kind of puts everything kind of neatly into a nutshell. Here we go. You know, we've got our n values, okay? In our n values, if we know n, we find L. What's our formula for finding L again? Yep, n minus 1. So we know if we are at 1, of course, there's only 0 is possible of L. 0 means it's an s orbital. So its subshell designation is going to be 1s, the energy level, and the orbital type. The possible values of M sub L then, of course, again, only 0. It's a sphere. It doesn't orient any differently in space, right? So we say there's 1 orbital in that subshell, total of 1 orbital in that first shell, that first energy level. And how many electrons can we have per orbital? 2. All right? So you know that there's 2 electrons. And if you look at the periodic table, how many elements do we have in the first period? 2. You know, so we have, you can look at the periodic table and you can start to see how this relates to, you know, if you have a periodic table and can understand what's going on, if your periodic table, you can get to where you need to be here. Okay? Obviously, you move down. So the next one, we've got the second energy level. We can have a 0 or a 1, so we can have either the 2s or the 2p orbitals, the subshells. And of course, we've got our various values for M sub L, which gives us a total of 4 orbitals in that shell. How many electrons can we contain in those 4 orbitals? 8. How many elements do we have in the second period? 8. Okay? Now, of course, it gets a little confusing as we go down through, because when you start getting into the dip, that's the D's, you know. So for what you guys need to know, for what we're talking about, that's really where you need to go with it. And those of you who teach it, I know, you know how to teach that part. So there's no big issues there. But you can use that, and you can verify your number of elements based on that. And really, when you look at, I'll give you another resource in a bit. But when you get into that third energy level, you've got your 3s, which of course is your sodium magnesium. Your 3ds do dip down and are the first row of the transition elements, right? The transition metals. And then jump back up to that third, you know, the rest of the third period. And when you count those up, how many elements do we have there? 18, because we've got all the groups. And we've got 9 subshells which gives us 9 orbitals, which gives us the 18 electrons. So you can see where it all develops. All right? All right, so the next thing we need to talk about is orbital diagrams. And we're going to look at the orbital diagrams. Here's a couple rules, and then we'll look at doing them. I think you guys will be fine understanding the rules. I've kind of skipped the rules for some of the other groups, but we're going to go over them. So, of course, we've got this electron shell. If we're talking a shell, we're talking about the electrons that have the same value of n. So the shells are, the layers of the onion, or the gobstopper analogy is the other one I like to use, right? Subshell. Subshell has electrons that have the same principal quantum number, n, and the same L value. All right? So you see a shell with a principal quantum number n will have exactly n subshells. And if we go back and look at this, we've got n, right? And we've got an n of 2, and we've got 2 subshells. So there's our, one of our rules we can look at. Of course, we got the orbital. The orbital deals with the wave functions that describe the spatial arrangements that we're talking about. If you get to the orbital, you need to know all the pieces of information to get to the orbital. You need to know the n, you need to know the L, you need to know the m sub L. That's what tells you that you're dealing with a 2px orbital or a 3d squared orbital. All right? And then finally, we can talk about orbital diagrams, which is what we're going to work on next. In an orbital diagram, each orbital itself is represented by a little square box, and you put electrons into those. Each little orbital contains how many electrons again? 2 electrons. So we're going to put them in is either spin up with the arrow pointed up or spin down with the arrow pointed down. So now, if we look at our energies of our orbitals, here's what we have. And we talked about this before. As we increase our principal quantum number, we're increasing our energy. Of course, you notice that you start getting into some of the anomalies, the 3Ds and the 4Ss switching. We're not going to go into the details of why that happens. The main thing is just understanding the general rule that we go from lower energy with the lower principal quantum numbers, higher energy as we increase the principal quantum number. You also can see here, we talked about the fact that we have a 1s. 1s is one orbital, contains again the 2 electrons, right? And then we've got, up in the second energy level, we've got the 2s and we've got the 2p orbitals that we can go ahead and start to fill. All right? You can see here a couple things. In a specific energy level, they're always going to fill s, p, d, f. Okay? That's always a rule. It's how it works. All right? The other thing to point out is when you have 3 orbitals that are at the same energy, they are called degenerate orbitals. Okay? So they have the same amount of energy, which means in terms of filling the electrons in, they're going to fill in a specific order at that point. They're all at the same energy, but we've got to go through and understand some rules in terms of how they're going to fill. All right, so here's our rules we have to follow. The first rule is the Pauli exclusion principle. Pauli exclusion principle tells us that no 2 electrons can have the same 4 quantum numbers. All right, they can have the same first 3, but the spin's always going to be different. All right. The other rule, again, we talked about each orbital, max of 2 electrons. It's a max. It can have 0, it can have 1, but no more than 2. And then finally, Hund's rule. All right, Hund's rule, it talks about the filling of the orbitals. And it says that we have to fill each orbital singly first before we go back and pair them up. And we'll look at that as we go through our examples here, what I mean by that. So what we're going to do, we're going to go through a couple examples. And again, this is some of the material that you're expected to know in terms of the core standards, in terms of what's on the test. So some of this is going to probably look a little familiar. All right, so we go ahead and we start drawing the orbital diagrams. We're going to do the first one together, and we'll explain it as we go. Again, some of you, it's going to be, common everyday material. Some of you, it's not so much, but please ask if you have some questions. As we go through this, we had looked at that energy, and we said they have to fill in specific order, right? What's the first orbital that we're going to fill? The 1s, yep. All right. And then we're going to go ahead next to the 2s, and then we're going to go to the 2p's. So if we find carbon on our periodic table, how many electrons do we have? 6 electrons. All right? So in our orbital diagram now, we have to take these 6 electrons we have, and we have to place them into this orbital diagram. So we said one of our rules was we start filling the lowest energy orbitals first, right? So we're going to put how many electrons into the 1s? 2. And we put them in that they have opposite spins. Again, no 2 electrons can have the same 4 quantum numbers. So these guys will have different quantum numbers because one will have a positive 1/2 for the ms, and one will have a negative 1/2. How many go into the 2s? 2. All right, it's still moving up in energy. Now we get to our 2p orbitals. How many electrons do we have left? 2. How do we have to put those 2 in? 1 each. From Hund's rule, we've learned that we have to put them in, and you have to put them in order, you fill each sublevel with 1 first before you go back and pair it up. So if you see a question that has this answer for carbon, it's wrong. All right? If you see an answer that looks like this, it's wrong as well. Right?
Is there any way to determine what spin it has if you don't fill up everything?
No. And I was going to say, that was the other thing I was going to point out for you guys. If you do see this, that's okay. They're all the same direction. Okay? So
They always have to be the same direction.
they always have to fill in the same direction. Yeah.
So explain to me again why there's 3 blocks in the P section.
Okay, so when we looked at that, we said it was 2p. So for p, what was our L value? Do you remember?
I have no idea.
Okay. That's from that little chart. If we look at this, we've got our n. Our n for this guy is going to be 2. For L, we said if n is 2, L can be what 2 options? 0 and 1. All right? An L of 0 corresponds to an s orbital. Okay? So that's our 2s that we're talking about here. Now, this 1 corresponds to a p. All right? But when we go to the next one, then we go to, let me erase the wrong answers. When we go to m sub L,
L is 11.
yep, for the L being 1, what options do we have for m sub L? Yep, -1, 0, and 1. So the reason there's 3 here is because you've got 3 options for that, for the m sub L. Okay? All right. We'll try to.
Build things and draw stuff.
It might
Okay.
visualize like this is the S.
I'm going there. All right. All right. All right. So let's go there more quickly. Actually, what I'll.
Explanation, not enough visual.
And everybody's a different type of learner, and I'm good with that. All right. What I'm going to give to you, and this may help you, is you need to take the top 2 pages. I did not staple them. I apologize. It's a periodic table. It's got some numbers in it, and then it's got a blank one that we're going to put all that, the S block, the P block, all that good stuff in it. Yeah. You know, if there's extras, I'll take them back then. I'm just kind of grabbing. All right, you need to take the top 2 of each. Actually, let me pull this. All right. All right, so my visual learners. All right. So we got this periodic table. What this periodic table shows you, this one that's got the letters and the numbers in it, is what orbital you're filling as you're at a specific spot. All right, so you can take that. I don't think it overlays I'm not sure that it overlays, but you can try to overlay it. If not, you can use your positional relationships.
Pretty good.
Is it pretty good?
Close.
Okay. So, but if not, you can find out that you have a carbon. And you can find carbon on the periodic table. You can find carbon on this periodic table. And see that it's going to be filling into a 2p orbital when it fills. All right? So you can see that there's going to be some trends that are going to develop here. If we look at this, and we look at the blank one, what we have is we end up with blocks. And in terms of what, oh, darn it, touched the wrong thing. All right, so we've got blocks that we can look at filling. When we talk about this block, this is our S block, we like to call it. All the electrons, as you look at the one that's got filled in information, are going to be filling into S orbitals, okay, as you go down through that whole block. When you go over to the side, well, of course, we got this little guy. Helium, right? Still has that S because it's at 1s2. When we get down to here, the big block on the right side is the P block. All right? The key to remember with the P's is that there's always 3 P's. Okay? And maybe if you memorize that, I mean, it might help to understand that if you don't remember the formula for figuring that out. Either way, it'll get you there. The other thing you can look at is that if you know you're filling the P block, right? How many elements do we have going across there? 6. So we have 2 electrons per orbital. So then how many orbitals do we have to have? You can get to your 3 that way. Okay? So that'll get you there as well.
Those 3 squares.
That's what those 3 squares are for.
And 2 guys can fit in that 3 squares.
Yeah, yes. The little electrons can fit in there.
Carbon's only the second one in.
It only has 2 electrons.
So you need 2 of them.
Yep. Okay? Okay. Did that help a little?
Yeah, I suppose so.
Okay, we'll do another one then too. In terms of filling in our information on our table, when you look at that information, this is just to fill the chart in. You do not need to know this unless you need to know it, okay? Unless you're teaching it. But the D block is this transition metal piece in the middle. To figure out what orbital you're on there, it's n-1d. So you see that on the nice filled in one, that first row across there are all the 3 Ds. All right. You'll also notice some asterisks. Those who are chem teachers know the asterisks are the exceptions, because while we like rules, we also like exceptions. Again, not critical for what you need to know from this, okay? Critical if you're teaching it, though, obviously. And then finally, the bottom block is the F block. And if you look at that, you can see that we get n-2F is the way that you figure out what orbital you're in there. Okay? So let's go back. It did kick me all the way out, so let's figure out where we are. All right. So let's move on and look at phosphorus. And I'll be honest with you, at a certain point, some of it you may end up memorizing to understand it. The more you understand about the periodic table, the more you realize that you really don't have it memorized anymore, that you use those, like you were doing the dividing, you use those tricks to figure out what's going on. Okay? So we're going to look at phosphorus. How many electrons does phosphorus have?
15.
All right. So again, we can look at, and we can find phosphorus on this nice little filled-in chart here as well. And you can see that ultimately you're going to be filling into a 3p as your last orbital that you're filling into. So now we just have to go ahead. We have to write our configuration, our orbital diagrams. First orbital again is our 1s. Let's write out all our blocks first. So 1s, then we're going to fill our 2p. Again, you can kind of work your way down this periodic table and see what comes next. So we've got 1s followed by 2s. What's the next orbitals we fill in? The 2p's, which is our 3 2p's. What's our next orbital? 3s. And then the 3p's. All right? So now we have 15 electrons to put into this. Of course, we start at the lowest energy, and let's start putting them in. How many electrons go in the 1s? 2. 2s again, 2. The 2p, how many electrons total do we get? 6. I will still go through and fill them and then pair them. Fill them singularly first and pair them back. Just good technique to get into. 3s, of course, we still have our 2. And how many are we left with at this point? 3. How do those 3 have to go in? Yep. 1, up. Each of them has to be up. All right? Again, you could see this as, is this correct? Would that be correct? No. Another option that you could see no, they've got to fill in the order they've got to fill in, right? That 3s has got to be filled before you're going to go on to that 3 piece. So again, yep, that guy's wrong.
Okay, so I have one last question.
You can ask more than one.
Okay. Each time that the P comes up,
Yes.
as we go down,
Yes.
you have 3 blocks.
For the P's, you're always going to have 3.
Always gonna have 3.
Yes,
Then the S's are always going to have 1.
correct.
And D's are going to have
5.
5.
But you're not going to have to worry about these, but
You
yes.
just go through and count. Like, okay, once you get past the S level, you're done. You go to the next S level.
Yes.
So on and so forth. And you just count.
Yeah.
Like binary numbers. You just count it.
You could do it like that, yeah. Yeah. Is that good? Does that help?
Right.
Good, all right.
What's the purpose of this?
Wow, you're a good student. How many times a day do you hear that? Although we're not the math teachers, so that they hear it probably more than us. When am I ever going to use this again? The main thing that you're looking at is that as you get into this and you get into the fact that you've got 3 electrons that are unpaired in this p orbital, that's going to contribute to how phosphorus is going to react with other materials. Ultimately, if you think back to high school, atoms like to have an octet of electrons. They're happy when they have their octet of electrons. It's one of the rules. And basically, they're going to want to find partners to these electrons. They're either going to give them up, or they're going to, they're either going to lose them, they're going to gain them. But they're going to react, and that's what dictates reactivity. So if you have an understanding of what's going on here, you can start moving into how does reactivity work. Okay? Because ultimately, sodium and chlorine react to give you sodium chloride because sodium has 1 valence electron, chlorine has 7 valence electrons. They both want to have 8. What happens? Sodium gives its 1 to the chlorine. There's all that at play, but that's maybe next year. Like, I haven't looked at the core standard for next year, but maybe next year. But ultimately, it dictates reactivity. So it is critical to, if you understand this, you can understand the next step. Okay? All right. The other examples I'll leave, and we'll come back to those later. Now, I've got a couple other analogies to show you. This is an interesting portrayal of how to show this electron configuration as well. It's from a JChem article. Those of you who teach may want to look at this article. It's kind of an interesting presentation on the material. It talks about housing electrons. All right? And basically what it comes down to is that each electron is going to have its own address. All right, so let's look at how it's developed. Each of the houses that we see on this little diagram, and he's got the houses on the energy diagram. It's kind of good. Each house has a specific principal quantum number. So this is house 1, principal quantum number 1. House 2, house 3, house 4. Okay? Each floor in the house represents the second quantum number, L. All right? So if we're talking the first energy level, we only have 1 floor because we only have 1 L value, right? It can only be an L of 0. When we move on to that second energy level, we now have the option of having L being 0, or L being 1. So we have 2 floors in the house. Finally then, each room is actually the third quantum number, the m sub L. So we know for this L being 1, we have 3 m sub L options. So there's 3 rooms on that floor. Basically, if you rate it relates it more to almost an apartment or a dorm. You guys are staying in the dorms, right? If somebody wants to get mail to you, what do they need to know? They need to know your house number. That's your principal quantum number. They need to know what floor you're on. And they need to know what room number you are. Now, it might be that you're on, in McLean Hall, room 227. All right, but that tells us McLean Hall, 2nd floor, room 27. All right, same thing with this. You can find it helps you to find an electron and where an electron lives.
So each one of those floors represents one of the quantum numbers.
Yes, the floors themselves are the L's. So here you see for the first energy level, we can only have 1 L.
Okay.
It can only be 0, so there's only 1 floor. When we go to n equals 2, there's 2 options for the L value. So there's 2 floors.
Okay.
Okay? And then when you break it down to the room, if on that 2nd floor we've got those P's, we said just what we went through, that the P's have 3 different m sub L's, negative 1, 0, 1. That's the 3 rooms that we're talking about. Okay? So that's another visual, kind of relationship. The other thing it does point out is how the energy levels really at some point do overlap, which I like his portrayal of that as well. And the gentleman in the article actually built models of this to help teach it. So if you do have to teach this and want another approach to teaching it, it's kind of neat. Okay? All right, so now the next step from this is that we talked about orbital diagrams. We can talk about electron configuration. All right? The two are very closely related. You'll see that if it's not familiar to you, you'll see that as we go through it. The electron configuration deals with the arrangement of the electrons in the atom. All right? And it's more or less a shorthand notation for talking about the electrons in the atom. All right? We're talking again about the most stable configuration being the ground state. Always whenever we talk about something most stable, we're talking about the ground state. The energies of the electrons are all in their lowest possible energies, and that's all we're worried about for the sake of what we're talking about. Now, we're going to go through and actually write these versus having me read that to you, because I think it'll make more sense as you actually see it. So, ultimately, this is a part of an electron configuration. And what you see is that as you write these, the numbers and the letters that you write correspond to those quantum numbers that we just talked about and correspond to the numbers of electrons. So 4, of course, that's our energy level. That's the N number. When we look at the P, we said P meant that the L was what? Yeah, there are 3 of them, but it's okay. 1. It's 1, but there's the option of having the possible of 6 electrons in it. Yeah. And ultimately, then the superscript is how many electrons are in that orbital. So if we take that and we look at this, this is a good relationship. These are most of the first period, and then we kick into sodium. So we can do our orbital diagrams. If we start at lithium, we have 3 electrons. Those 3 electrons start by going into the 1s. 2 of those go there, 1 go into 2s. Okay? When we go to write this as an electron configuration, again, the way you do it is basically you're taking this configuration and you're writing this out into a different notation. So the first thing you do is you tell me about the orbital. So we've got a 1s orbital. That's our first orbital that we encounter. How many electrons are in that 1s? 2. P is just, I don't know that there's a word for it. It's just P. It's just S, P, D, F. And they actually keep on going, like if you would have, but you only need to really be concerned about SPD in that regard. Okay. I don't know. I don't know that it.
There is something, but I don't.
But I was going to say, and we never talk about it because you just talk about it as a P and you visualize what a P is from that. Yeah. So keep it simple, right? We're good for that. All right. So we got our 1s, and we had 2 electrons in that 1s orbital. The next thing we need to write is we've got a 2s. How many electrons do we have in that 2s orbital? For lithium, just the one. So its electron configuration becomes 1s2, 2s1. Tells you a lot about that. You can also look at this and go, all right, we said there's 3 total electrons. If you add up your superscripts better add up to 3. All right, you need to account for all of those electrons. As we go down through, you can see here's our carbon example that we did. It's a 1s2, 2s2, 2p, and how many electrons do we have in that 2p? 2 electrons. All right. We're going to jump down and we're going to look at, actually we're going to go all the way to sodium. So if you look at sodium, sodium's got 11 electrons. Okay, it's the first element in the third period. Again, so we can go ahead, we can draw its configuration. Always start with 1s, right? We've got our 2 electrons in 1s. Our 2 electrons in 2s. 1, 2, 3, 4, 5, 6 in our 2p. And we've got 1 electron, of course, in our 3s. Yes?
Sharp principle.
Ah.
That's the sharp principle diffusion fundamental.
Okay, thank you.
Who cares?
Yeah, it's P. Okay, it's going to say, yeah. And we just teach it as P, really, but thank you. That's good. All right, so here is our orbital diagram for sodium. Okay? If we go ahead and we convert that into an electron configuration, again, we write your orbital, 1s, 2, 2s2, 2p, 6, 3s, 1. All right? Now, that is correct. If you add up your electrons, you've got your 11 electrons. You will also see another notation for this, and it's the shorthand notation. What we do with this is we look at the periodic table, and you find the noble gas that ended the last period. So what is the noble gas before sodium? Neon. It is neon. So the way we can write this is we can take brackets. We can put the symbol for neon in brackets, and then we can add 3s1. What this tells us is that here's the configuration for neon, which we know is that. And it gives you then what become your valence electrons, which is a terminology. Valence electrons are what's important to reactivity as we move on. Before it, radon. And then what would be the little tail we'd have to add on? 7s2. There we go. Absolutely. Because you need to talk about all the electrons. This is just the valence part. It's just what's going to be involved in reactivity, but all the electrons are in the atom. So, yes. Okay, so you can just take whatever the element is, so the sodium example, and you can look for what was the noble gas that was in the period before it. So if you find sodium, it's the first one in the third period, so look at the end of the second period. So that becomes neon. And then we just take our neon, we put our neon in brackets, and then we just add what other electrons do we have besides that? Well, we have a 3s1 electron. That's it. So just like when you go down through and you find radium, which is the 7th period, second element in. Like I said, by that point in time, you don't want to be writing a full long thing out. Plus, then you get into all the having to know what comes next, which is a pain. All right. Did that help? So I have one more thing to briefly cover with you, and then I know you guys are supposed to leave here, I think, a little early. Yeah, I was going to say, I think you're supposed to go early so that you can go to lunch. I don't know. Well, yeah, I know, but they wanted to do something funky, though, with I don't know. All right. Okay. They told me something and cut it 5 minutes short. Okay. All right. Here's our periodic table. It's another visual. It's a nice visual in that, yes, here are those lanthanides and actinides put in place. You quickly see why you would never have a periodic table look like this, be a practical periodic table. The other thing, it goes back to what you asked about the SPDF. You can clearly see the blocks still on here. I mean, that's nice, nice separation. All right, now, the last part of this, I'm going to jump ahead. You can look at the slides. We talked about the emission spectroscopy when we started talking about the models. And I'm actually going to go to this. As I said to you, you can look through what's called a spectroscope. I have some tubes here. I was going to do it as a demo, but if you've ever used these, you know this room is not a good room to be doing this in. We've got a little diffraction grating and a little slit. We can look through the tube. You can look at any light source. Ultimately, when you look at that, you're going to see this pattern of bands of light. These bands of light correspond to specific frequencies. Those frequencies are related to the energy changes between the electrons. And the important thing to note is that each element is going to have its own signature. It has a very distinct emissions spectrum that you're going to be able to see. And again, it's useful in identifying, it's what they've used, you know, not the paper towel tube ones, but to figure out what's in the stars. The important thing to note from this, though, is that if we go back and we look at the theory again, is that these bands of light that we see are due to these discrete changes in energy, and they've got to be whole increments, okay? So you can't, again, you got to go from, you know, we're talking about we excited the electron. When you're looking at the emissions spectrum, you're looking at what happens when the electron falls back down. That's the light that's being given off. And again, that frequency is proportional to that energy that you're talking about. And again, it's got to have those distinct increment drops. So I know that's one of the questions that you guys will need to know as well. But it all deals with that, which we talked about earlier. But again, you can see, for those of you who've ever done this, it's easy to do it with the neon tubes, which is what we typically do. You can actually do it with flame tests, but it is extremely difficult to coordinate. I had 2 of my majors last year. We were trying to do it, and to try to do it for the non-majors class, and we gave up. So, all right. So that is all the material. As I said, I apologize for it being whirlwind, and I will have some stuff for you guys to look at. I kind of have, especially for you, those of you who are chemists, a little bit hokey video for you to watch the next session. It's about a half an hour. It's a little dated, but it's got really good reinforcing information to what we just talked about in it. And then we'll get you some practice and then looking at those apps and stuff as well. Okay? And please feel free, if you have any questions, feel free and email me. That's probably the easiest way to get in touch with me. Okay? All right, thank you.